A very good morning to you, ladies and gentlemen. It is my pleasure to welcome all the participants for the Marine Engineering session of the 14th International Research Conference of General Sir John Kothalavala Defence University. Now you are here with us in the Marine Engineering session based on the theme of confronting challenges and uncovering solutions in marine engineering in the new normal. This session will be chaired by Dr. T.A. Piesiri, while the rapporteur will be Cadet Sergeant R.G.Y.A. Rajapaksha. Prior to the commencement of this session, I would like to give a brief introduction to our chairperson. As a graduate from the University of Sri Lanka, Katubedda campus, Dr. Piesiri joined the academic staff of the Department of Mechanical Engineering of the University of Moratuwa as an assistant lecturer in April 1977. In 1981, he was granted a Commonwealth Academic Staff Scholarship to read for Masters in Marine Engineering at the University of Newcastle upon Tyne, UK, where he completed a master's degree followed by his doctoral degree. While serving as a lecturer at the University of Moratuwa, he again went to the Directorate of Marine Engineering Training in Mumbai, India, for a one-year training program in marine engineering. There, he excelled in his studies and completed the training, winning the Best Student Award. Upon his return, he was entrusted with the responsibility of developing the marine engineering program for the National Diploma in Technology. Dr. Piesiri was a key figure in developing the NDT Marine Engineering Program and later the NDT Nautical Studies Program, and he was promoted to the grade of Senior Lecturer in 1991. Dr. Piesiri's capacity as an engineer, a planner, and an administrator was identified by the UGC and recognized in the educational spheres. For a short time, Dr. Piesiri served as the Director of Industrial and Technical Studies at the University of Moratuwa, overseeing all NDT programs prior to his appointment as the Director General of the Institute of Advanced Technological Education. He held this post for 2 years from January 1999 until January 2001. After the tenure as the DG of SLIATE, on his return to the Moratuwa University, he was the obvious choice for the post of Director of the newly formed Institute of Technology at the University of Moratuwa. His tenure at the Department of Mechanical Engineering after handing over the ITUM to his successor in 2004 was short. He was then appointed as the DG of the Tertiary and Vocational Education Commission in June 2004. Over the 7 years of his tenure, the formation and introduction of the National Vocational Qualification System is one of his significant contributions that brought the entire technical education system under one framework for the first time in Sri Lanka. However, he was continuously involved in various national level committees working on educational reforms, such as the development of the Sri Lanka Qualification Framework to bring all educational qualifications under one umbrella. Dr. Piesiri reached the pinnacle of his career when he was appointed as the Vice Chancellor of the University of Vocational Technology in January 2013. There, he completed his full term of 3 years as the Vice Chancellor and ensured smooth sailing for his successor. To sum up Dr. Piesiri, a person meticulous in his approach towards work, a person who is methodical to the core, a person who is humble and quiet, yet objective, a person who never ran behind monetary benefits, a family man, and last but not least, a person who has immensely contributed towards the development of the education system of Sri Lanka. While we thank our presenters for their kind contribution in making this event a success, now we cordially invite Dr. T.A. Piasiri to commence this session. Over to you, sir.
Thank you very much. Presenting author is Commodore MCP Dissanayake. Commodore Dissanayake is currently performing at the head of the department, Marine Engineering, and holds 2 patents for his research papers published so far. He is an inventor and has published 6 publications on brackish water reverse osmosis application, fan boat and oscillating water column ocean wave energy converter. For director in research and development at Sri Lanka Navy and has received commendations on several locations from the Commander of the Navy and from His Excellency the President of Sri Lanka for his innovations. Further, he was awarded the prestigious Japanese Sri Lanka Technical Award for his own developed low-cost reverse osmosis plant to eliminate chronic kidney disease from Sri Lanka. Moreover, he has vast exposure to marine diesel engines and possesses a master's degree in marine engineering from Australian Maritime College, University of Tasmania, Australia. Now I cordially invite Commodore MCP Dissanayake to make his presentation.
Good morning, ladies and gentlemen. Today I am going to discuss verifying of Orifice plate connecting duct lengths to validate performance of a vent test rig at Australian Maritime College by computational fluid dynamics as part of oscillation water column power takeoff. My outline is as follows: how oscillating water column ocean wave energy converter works, vent test rig, experimental recommendation, alternative method, geometry of pipe, generator mesh and boundary condition, comparison of experimental results with computational fluid dynamic results. Conclusion. Oscillating water column ocean wave energy converter consists of 2 major components. First part is chamber that absorbs energy from ocean waves and converts them into low pressure pneumatic power. Second element is turbine that runs by above developed pressure variation and drives a generator through a mechanical shaft and generate the electricity. In this process, turbine is exposed into unidirectional airflow and utilize one-way valve to escape air from the chamber. Vent test rig. A servo-motor operated vent test rig was comprising with 3000 mm in length and piston diameter of 1500 mm chamber, generate the basic airflow features of an OWC ocean wave energy extraction. The vent test rig was right scale and set up with volume of 3.534 meter cube. Though the upstream and downstream of duct length of vent test rig were not matched with given specified standards due to space restriction. Experimental recommendation. Expected outcomes could not achieved by the experiments due to space restriction of the room. Alternative method. Chose computational fluid dynamics application as alternative method to continue the investigation with economy of effort. My aim. The objective of this investigation was to apply CFD instead of vent test rig experiment and carry out modeling, then compare outcomes with experimental results. Condition 1, CFD application was used to test differential pressure across the orifice plate with same upstream and downstream length of pipe that utilized during the vent test rig experiment. In addition, CFD was applied again for the specified lengths of pipe with same orifice plate to measure the differential pressure across it. That is condition 2. This is the geometry of the short pipe. This is the condition 1. The upstream and downstream pipe lengths were taken as 1675 mm and 1800 mm respectively. This is the long pipe. This is the condition 2. Upstream length increase up to 3000 millimeter and downstream pipe length kept as 1200 millimeter as per the standards. The 3D geometry of two pipes and orifice was generated by inventor software and exported into the ANSYS 19.1 workbench software. Subsequently, a fixed diameter orifice was made and selected XYZ coordinates correctly. Then develop upstream duct length up to 1.675 meter and downstream duct length with 1.8 meter as condition 1. Then simplify the geometry by introducing the inlet, outlet, walls, orifice inlet, orifice outlet to the ducts and orifice. Similarly, upstream duct length was extended up to 3 meter and downstream duct length was shortened to the 1.2 meter as per the standards. Consider as a condition 2. Generate a mesh. Then after that we generate the mesh through the ANSYS 19.1. This is the short pipe. This is the long pipe. The process of meshing is time consuming and complex affair to generate an accurate mesh. The mesh is essential to be quality to give accurate answers. The movement of flow is bit complex in this application. The mesh files were imported into CFX presolver and conduct the analytical study. Then define the properties of air and boundary conditions. The two numbers of monitoring points are established with 0.15 distance from the orifice plate inside the upstream of the pipe as per specified standards. Similarly, two more numbers of monitoring points were set up with 0.75 meter distance from the orifice plate inside the downstream of the pipe to obtain relevant measurements of the pressures. The mass flow rate was calculated as per piston moving velocity and fed as input to the application and obtain the related pressure by monitor points. This is the boundary condition of short pipe. You can see here inlet, orifice plate and outlet. The close to the orifice plate, there are 2 points. Those are the monitoring points. Boundary condition of long pipe. The inlet and outlet domains were modeled and with an air in 3 different velocities. The inlet and outlet pressures were monitored through the monitoring points and carry out the simulation. Then it ensures to get the convergence in inlet pressure variations along with velocities. This is called convergence study of short pipe. This is there is another name for this, that is the study to prove the boundary conditions of the generated mesh. The inlet pressure is converted with an estimated error of 0.0352, 0.21 and 0.175 for the coarse, medium and fine mesh respectively. In this table, you can read this table in 5 columns starting from types of mesh, number of nodes, number of elements, size and inflation thickness. And we considered 3 measures, coarse, medium and fine. It was revealed that the fine mesh providing the minimum error compared to the other measures. Fine mesh giving the minimum error. Thus, the fine mesh was designated to conduct the analysis process. The plot is clearly specified that highest inlet pressure at fine mesh, then second highest inlet pressure at the medium mesh, and finally lowest inlet pressure at the coarse mesh. Grid convergence study inlet pressure. This is the graph we obtained during the CFD modeling. This is for the short pipe. Convergence study for the long pipe. Condition 2. You can read this table in 5 columns, similar to previous slide. Types of mesh, coarse, medium and fine. The inlet pressure converged with an estimated error of 0.04, 0.0395 and 0.39 for the coarse, medium and fine mesh respectively at the velocity of 0.25 meter per second for a long pipe. It was revealed that the fine mesh providing the minimum error compared to the other measures. This is the grid convergence study, inlet long pressure. These are the results we obtained for the short pipe. Here you can read this table in mainly 3 columns: velocity, P1 inlet, P2 outlet. In P1 itself, there are sub 3 columns, that is CFD, computational fluid dynamics outcomes, EFD, experimental fluid dynamics outcomes, and percentage error. We selected 3 velocities, which is similar to the experimental. Here you can see the percentage error of the inlet, the minus 2.53, minus 1.77, minus 0.57, and P2 outlet. Also, the percentage error is very minimal. Here you can see the pressure planes which we obtained during our modeling. Results of velocity of 0.25, 0.15, 0.06 meter per second in short pipe. If you see the pressure plane close to the orifice, you can see the difference. This is the assessment of experimental outcome versus CFD outcomes of inlet pipe. And there is no big variation. It is very minimal. That means the inlet pressure or the inlet pipe or the upstream pipe which we modeled through the CFD is correct. This is the outlet pipe, assessment of experimental outcome and CFD outcomes of outlet pipe. Here also the error is very minimal. That means our model CFD pipe was correct. With that, comparison of pressure for the long pipe. We couldn't have experimental outcome of the long pipe because of the space restriction. We did everything through the CFD simulation and obtained the results. You can read this table in 3 columns: velocity, inlet, and outlet. For the 3 velocities, 0.06, 0.15, 0.25. These are the pressure planes outcome during our modeling. It is revealed that the pressure development through the orifice plate was high when the upstream pipe was the short and uniform flow of outcome was showing due to the sufficient length of downstream of pipe. These are the results we obtained during the CFD simulation for the long pipe. Conclusion: the CFD application was proven that specified duct lengths are directly impacting to performance of vent test rig and decreasing the generating pressure along with the length of the pipe due to relative roughness. Thank you very much.
Thank you very much, Commodore Dissanayake. A very enlightened presentation on modeling using computational fluid dynamics. Very well done. We will take the questions at the end of all 4 presentations. May I now present the second presenter? The title of the paper is "A Hybrid Diesel Engine Simulator as a Skill Development Tool for Marine Engineering Undergraduates." This is done by the panel of authors, and the presenting author is Lieutenant Commander VADJV Perera. Lieutenant Commander VADJV Perera is presently serving as a lecturer in the Department of Marine Engineering, Kotalawala Defense University, and possesses a BSc in Marine Engineering from KDU with a second-class upper merit. He has vast experience in maintaining medium-range marine diesel engines, shore-based diesel generators, and air conditioning systems. Further, he is a competent engine room watchkeeper and interested in marine propulsion, engine control systems, and microcontroller-based automated systems design. He is a member of Royal Institute of Naval Architects, an associate member in Institute of Engineers India, and possesses the accreditation of Chartered Engineer India. Over to Lieutenant Commander Perera for your presentation.
Thank you, sir. Session Chair, distinguished audience, good morning to you all. I, myself, together with the members, will be presenting on the topic, a hybrid diesel engine simulator as a skill development tool for marine engineering undergraduates, which is based on the marine diesel engine simulator established at Department of Marine Engineering, Athukorala Defense University. The aim of this paper is to discuss the prospects of using an engine simulator for enlightening undergraduates through a simulated environment. The scope of my discussion will be listed on the screen. Qualitative advancement of the learning is a progression at university domain, and marine engineering education depends mostly on the developments of hands-on skill training sessions and educational software. Therefore, this hybrid diesel engine simulator is designed to conduct realistic engine room scenarios and performance evaluation of the current technical state of engines and devices. Further, this platform provides facility for marine engineering undergraduates to develop skills on management, operational, and supporting activities through imparting knowledge and confidence in a much efficient way. Therefore, as in nutshell, it is the ambition of developing a qualified marine engineer as an onboard engine room watchkeeper by simulating realistic scenarios inside an engine room. Such scenarios are designed in such a way to get rid of operational fears of a watchkeeper, increase confidence in operating and managing engine room resources, enhancing teamwork skills onto decision making and emergency response. Most of engine room malfunctions are occurred due to operators' negligence and incompetency or human errors. Therefore, hybrid diesel engine simulator is mainly pursuing to become a perfect teaching method to train modern ship's crew by assessing the watchkeeper's behavior in emergency or crucial situations, enhancing practical knowledge on previously acquired theoretical aspects, improving the ability on problem solving, and components identification for replacement. Systems and subsystems. The entire system comprises with 4 major functional subsystems shown in the slide. Simulation control and actual control system are incorporated with human-machine interfaces known as HMIs, and the local control system is based on a microcontroller-based platform. Sensor inputs such as starting air pressure, freshwater temperature, lubricating oil pressure, seawater temperature, fuel pressure, and exhaust temperatures are obtained by the local sensors along with the functional inputs from the machinery. The output function of the microcontroller will be in accordance with the algorithm provided for the functionality. All records of the training is stored in a separate memory location within the system, and authorized personnel with a password has the accessibility. Now we will look into the system specifications. The facility comprises with a 6-cylinder main engine which can provide 850 horsepower. Separate consoles are available for instructor and trainees to control the accept simulations by alarms. Here, the instructor's console is enabled to interchange the entire system into 2 modes, namely simulation and actual. All simulated activities are done in simulation mode. Further, these consoles are enabled with fully duplex wireless communication with the microcontroller at local control panel. The local control panel comprises with the microcontroller and raw inputs from the local sensors. Apart from these components, the facility comprises with a high-pressure air compressor which can produce 30 bar, a fuel transfer pump, cooling pumps, standby lube oil pumps, and freshwater lubricating oil coolers, and a fuel oil tank, which these components are common to any onboard engine room. With the outset of developing competence and skills of trainees, activities related to functioning of a main engine is developed. Such activities are standard pre-start checks which are carried out before starting the main engine, such as oil level of rocker lube oil, turbo oil, engine lube oil, fuel oil, cooling water level of expansion tanks, opening of system valves, visual inspection of engine and hand turning of main engine, and sequence of actions to be carried out in starting the engine, such as confirmation of interlocks, confirmation of starting conditions such as reaching adequate starting air pressure, lubricating oil pressure, and fuel oil pressure, and etc. recording the data acceptance of alarms and situation identification, such as monitoring of engine behavior, abnormal parameters, noises, excessive vibration, and identical machinery malfunctions, and the stopping procedure, post-operation inspections and shutting down, such as interchanging of controls between remote and local, unloading of engines, and so on. As an example simulation, it was considered the activity in identification of exhaust temperature rising in the engine within the simulated environment. The objective of this activity is to make the trainee observe about the abnormal temperature rising in selected cylinders through the recorded parameters and other supporting parameters. During this experiment, students recorded the subsequent parameters together with cylinder exhaust temperatures. Since the engine was in simulation mode, the rest of parameter readings were obtained as simulated values for respective RPMs. Such values were generated compared to possible temperatures in an actual scenario. Accordingly, obtained temperatures were tabulated in a graph as depicted in the slide, and variation of temperatures were the key consideration for the trainees to discussion. So with this result, the trainee should be able to identify the abnormality of exhaust temperature ranges in number 2 and number 5 cylinders and identify the root cause which will lead to such occasions. Further, it is discussed about the supporting factors to confirm the root cause, such as observation of black smoke, low charge air pressure, and so on, which are some of observations pertaining to the given root cause in the slide. Thereon, the discussion further extends to carry out possible actions in down-to-top approach, whereas carrying out remedial actions from the most possible action to the least possible action. So as a conclusion, this simulation facility is equipped with 2 workstations for an individual training and control of the watchkeepers at the same time. Therefore, enlightening marine engineers by the means of hybrid marine engine room simulator is the least expensive and the safest training and evaluative method in the present day context. Accordingly, trainees can evaluate performance of changes for selected active and economic parameters of the Nigata 6M2X AGT marine diesel engine operation and fuel supply system. Further, trainees are highly involved in measuring, computing, and presenting the data. Therefore, the analytical skills are directly developed as engineers. So this is the end of my presentation, and thank you very much.
Our next presentation is on the design approach to optimize waterjet performance, a case study, Coastal Craft Sri Lanka Navy. This is jointly authored, and the presenting author is Commander D.S. Bogahawatte.
Design approach to optimize waterjet performance, a case study, Coastal Petrolcraft Sri Lanka Navy. If you can remember the ship jetliner, above figure depicts its waterjet model. The waterjet sucks water and throws from stern. As a result, hull moves. Also, you might familiar with traditional propellers, but our study is based on waterjets. So the marine propulsion system usually consists of marine engine, gearbox as optional, propulsion and a hull. So the hull and propulsor studies with thrust, propulsion engine studies we do with power. So the naval architect key to ensure power transmission, power output, RPM, and finally to pitch the propeller to ensure optimum performance of the system at the equilibrium condition. So we need to first study propeller theory. These are based on models defining non-dimensional coefficients. So the non-dimensional coefficients are the pathway from a model to actual ship. So the thrust coefficient, torque coefficient, and advance coefficient are being used. And these are for the propeller selection for conventional screw propeller. So all these three will the combination of thrust, torque, advance velocity, diameter, RPM. So these are the typical plots, and it offers successful methodology which offers benefit of number 1, work with factors rather than broad 3G geometry. And number 2, simple to calculate yet all-inclusive board performance studies. Thus, this numerically simple task leads to successful selection of optimum parameters for propellers, amounts to RPM, diameter, pitch, and so forth. Earlier plots are for the open water propellers, but our study is for water jets. And this is the figure that we receive from the waterjet manufacturer. So the green curves are the hull resistance, and blue and red curves plots are power delivered by the engine, typically at 85% and 100% RPM. So this approach by the manufacturer hides the RPM power relationship, and it does not allow the computation and analysis of fuel economy, boat acceleration reserve for maneuverability and comeback, which is very critical in naval applications. So non-availability of comprehensive study approach, which uncover all parameters for military applications with waterjet propulsion was the problem statement. Moving into the objectives, to seek the reduction in craft bare hull drag, to promote an adequate analysis of engine RPM, to understand the availability of full rated engine power absorbed by the waterjet. Thereby, employment of universal waterjet coefficient has been considered to design and to eliminate the flows associated with the traditional thrust resistant plotting technique. So a naval project designed by authors used to demonstrate how authors avert possible complications and optimize the design through a new calculation methodology. So this is our project. 20 meter length, 5 meter breadth, 27 tons of weight, which goes at 35 knots, made out of GRP material. Obviously, waterjet selection with certain criteria: power to weight ratio, board speed, transom detail of the hull, GRP as the hull material, and robustness for naval application. These are coming from the operation departments. On top of it, technical requirements, waterjet specifications we studied: nozzle, impeller, physical characteristic, ratings, impeller thrust curves, which all combine in our studies. When moving into the studies, we knew trimming of the boat of is prime importance. So this red curve is the trimming curve which is important, and the black color curve is the hull resistance. If the longitudinal center of gravity is too far forward, the power requirement to reach the planning condition would increase. On the other hand, if it is too far aft, dynamic instability called proposing would occur. So we studied, and studies indicated that a trim angle between 3 to 5 degrees would be the ideal balance for this coastal petrel craft. And most importantly, we do not want to install any trim tabs. So these are the typical waterjet curves we receive. If you see the LCG and the dead rise angles, which are on red color, those are the sensible parameters. We asked for these plots from them, and we identified drastical deviations on the resistance curves. So figure depicts a considerable resistance near 20 knots. So that is the transfer of forces from hydrostatic to hydrodynamic, with a wide flat region of same hull resistance up to 32 knots. So the naval application with extreme maneuvers as the primary design objective, it is required to operate the boat above this transition region. This analysis revealed boat parameters improvement is a necessity. So further, this approach not allowed the visibility of acceleration reserve and efficiency of this operation. Thus, authors opted for complete system analysis with universal waterjet coefficient, which was initially proposed by McPherson in their 2010 studies. And these are one software that we use, the NavCAD. 7 principal geometric parameters are listed in the upper table. Length, beam, and depth were fixed for this project for the operation department requirement, but we were interested to see how the parameters change with respect to longitudinal center of buoyancy, gravity, and flotation. Also transom immersion on the hull drag. So with all these studies, the first objective of seeks to reduction in craft bare hull drag achieved. This is the plug development. We incorporate all these things into the plug development. Then moving into the next 2 objectives of our studies with the universal waterjet coefficient. One coefficient is the power coefficient, other one is the thrust coefficient. This is how it has been derived in simple terms. Then moving into our studies, and earlier depicted conventional thrust curves, which are generally given by the manufacturers, were collapsed by authors into 2 coefficients called CP and CT. And as placed in this figure, since the operating region of the coastal petrel craft, which goes at 35 knots, lies in the region of small and small y values, waterjet selection could be justified for high-speed operation. Then one research outcome with employing universal waterjet coefficient was the ability to identify operational location of maximum jet efficiency, which was 56% for our case. And for current available naval boats, what we have, this figure is between 52 to 55%. So these are the traditional curves what we received, but now it is probable to select the best performing waterjet with greatest efficiency. So we redefine the curves with efficiency coming into the play. The author design is closer to maximum possible waterjet efficiency. That selected waterjet is the peak efficiency at high speed, which was the requirement. These curves also indicated that a speed of 35 knots would be the ideal operating point for this craft. And this is one of the important case, power and RPM curve, where we study maneuverability. The upper curve indicates the delivered power by engine, and below curve is the absorbed power by the hull. At around 1500 RPM, power reserve is available for naval maneuvers. Further, we propose to shift the curve, power absorbing curve towards left side bit to increase by the pitch to catch the few more knots. So the Waterjet manufacturer agreed to deliver customized impeller for our naval application. And most importantly, the vessel acceleration. The acceleration analysis with a similar Waterjet model from another manufacturer was plotted. The Waterjet selected by authors took 20 seconds, where other similar unit took 22 seconds to reach 20 knots. But most importantly, to reach the speed of design speed of 35 knots, the selected Waterjet only took 32 seconds, while the other unit took 62 seconds. This information is very critical since this is a military patrol boat, as the time to reach its maximum speed of vital importance. Because we don't understand this concept, during the humanitarian law, we lost many boats. Hence, this approach of assessing the Waterjet performance using universal Waterjet coefficient is justified. And also we study the cavitation. So the red mark indicate where our operating point. So it is well away from the cavitation and in the blue screen. And to Jane's Navy International magazine also understand and the boats that built by us. And during my 6-year tenure at boat building yard, we started export boats to the Nigeria and to the Seychelles, and we earned a lot of foreign exchange to this country. And recently, Zambian Army commander, Zambia having a lot of large lakes, came to our facility, and this is the mold that we are going to build our boat. He inspected, and he is a potential customer. We will bring foreign exchange to our country. And as a conclusion, even though most Waterjet looks suitable for particular application, Waterjets are usually optimized for the manufacturer for separate application. The appropriate selection is the duty of the boat building yard naval architect. The actual naval patrol craft design engineering example discussed at this juncture demonstrate why naval architecture shall have dependable techniques to assess Waterjet performance. Traditional methods are beneficial to ensure particular Waterjet will meet some performance requirement, yet approach usually inadequate for many critical assessment of Waterjet performance on efficiency, acceleration, entire RPM envelope operation, and so forth. So the authors exhibit how to employ universal Waterjet coefficient as methodology, which guide and point the way to accurate propulsor choice. The outcome is authors found the correct matching point, or in the simple term, hull, propulsor, and engine matching was done. And these are the few references, and the acknowledgement goes to the Sri Lanka Navy allowing us to do this project. And thank you very much.
Our next presentation is chronic kidney disease of unknown etiology in Sri Lanka, an implication of optimizing recovery ratio of brackish water reverse osmosis plant. This is the presenting author is Commodore MCP Dissanayake, who made the first presentation of this session. So I will not go into to introduce him formally again, and I would cordially invite Commodore Dissanayake to make the presentation.
Chronic kidney disease of unknown etiology in Sri Lanka, an implication of optimizing recovery ratio of brackish water reverse osmosis plant. My outline is as follows: global water crisis, prevalence of chronic kidney disease of unknown etiology in Sri Lanka, function of brackish water reverse osmosis plant, recovery ratio of existing brackish water reverse osmosis plant is calculated and identified as 50% of feed water. Mandatory requirement of 75% recovery ratio of brackish water reverse osmosis plants as per United States Environmental Protection Agency, recovery ratio optimization. Global water crisis. 785 million people lack access to safe drinking water. That is 1 in 10 people on the planet. Women and girls spend an estimated 200 million hours carrying water every day. What is chronic kidney disease of unknown etiology? In this disease, there are two types. Chronic kidney disease, or the CKD, is a long-term condition where the kidneys don't work as well as they should. It's common condition often associated with getting older. Chronic kidney disease of unknown etiology is a complex form of disease and disable the kidney function. The significant root for the CKDU has not yet been recognized. However, it is believed that changes in certain number of drinking water quality parameters due to contamination of water source by agricultural activities can be one of the root for the CKDU. Therefore, the government of Sri Lanka realized the importance of supplying safe drinking water as an appropriate method to curtail the CKDU spread in country. Prevalence of CKDU. In this map, you can see there is a reddish color area. One is Anuradhapura district, other one is Polonnaruwa district. Both the districts belong to the North Central province. These are the areas for the most vulnerable for the CKDU patients in Sri Lanka. Function of brackish water reverse osmosis plant. Before we are designing a plant for one particular location, we have to check the water source and test the water samples from Sri Lanka Water Board or Industrial Technology Institution. Starting from the raw water. Once the raw water comes into the feed water tank, normally feed water tank we are installing 5,000 liter tank. Then we can pressurize through the feed water pump. The feed water pump is normally centrifugal pump, which can be pressurized up to 3 to 4 bar. Then pressurized water goes to the multimedia filter. Multimedia filter is comprised with one sand filter and one carbon filter. Then pre-treated water goes to the cartridge filter. Cartridge filter always depends with the local market availability. Sometimes we are installing 20 micron filter, sometimes we are preferring for the 10 micron filter. It depends with the market availability. Then pre-treated water goes to the high pressure pump. High pressure pump is the heart of this application. In Sri Lankan context, we are using centrifugal high pressure pump for this application due to economy of effort. If we are moving to the global context, they are preferring to install the positive displacement pump due to durability. This pump pressurizes the water up to 15 bar. I want to emphasize one more fact. In Sri Lankan feed water, bit better than the what is available in other regions of the globe. Then the pressurized water goes to the RO membrane. RO membrane purified the water. Then product water goes to the product water tank, that is 1,000 liter shell tank. Then concentrated water or the reject water goes to the atmosphere. There is a separate CIP cycle is here, that is fixed with the application. When the membranes are getting clogged, we can operate this and clean the membrane and reuse it. My objectives: determining the water quality through a feed water characterization, designing a suitable stage array filtering membrane system to improve the recovery ratio up to 75%, determining the optimum output pressure at the concentrate output of second stage. My methodology: selecting implementation area, feed water characterization, membrane arrangement design, analysis specification of high pressure pump, standardizing concentrate pressure for maximum recovery, implementation. Selecting implementation area. MS Rashi Water was facilitated us to carry out research with their BWRO plant at number 407 Megaskama village, Talawa Divisional Secretariat, Anuradhapura district and North Central province. I was considered, while I was selecting this village, number of CKDU patients in the village, that was 745. Number of beneficial families from this existing RO plant, that is 550 families, and feed water source. This place is a bit far away from Colombo, 205 kilometers from Colombo. Feed water characterization. In this table, you can read this table in 5 columns, starting from parameter, the second and third SLA 614 standards, the fourth one results relevant to the sample, the fifth one method of testing, color. The color was 15, that is maximum value of standard values. The turbidity, NTU, 3, it is above the standard values. pH value, TDS, chloride, total base or calcium carbonate, total solubility, nitrate, nitrite, sulfate, fluoride, total phosphate, iron were less than the standard values. Then free ammonia was not detected. Then you can say, what is the requirement of doing RO for this particular location? You are right. But I did another sampling testing for the water, heavy metal detection. You can read this table in 4 columns, starting from parameter, CAS number, results, limit of detection. Arsenic, calcium, copper, chromium, iron, lead, manganese, nickel, potassium, and silver were not detected in that sample, but magnesium, sodium, and calcium were above SLS 614 limits. I want to emphasize one thing. If the magnesium is available with your drinking water, what happens? You will be having bitter taste. Because of that, we decided to incorporate my improvements with this existing plant. According to the theoretical aspects, there are 2 types of membrane arrangement. One is parallel, other one is serial. Here you can see just after the high pressure pump, you can fix the membrane parallelly and you can take out the permeate or product water. The serial arrangement, just after the high pressure pump, element 1, that is membrane 1, fix the second element with serially. There is a specialty in this. The output of element 1 will be the input of element 2. Pressure vessel arrangement before stage array of this existing plant. We studied the plant that was 5,000 liters per day plant capacity with a single membrane. Then we studied the specification of high pressure pump. It was a centrifugal pump, single phase, and can be pressurized up to 15 bar. Then I asked my students to practically work with this application and install the second membrane to the first one in serial method. But we couldn't able to get the product water out. Then we did a modification, tap in the feed water and get the feed water out and incorporate with the element 2 input. And there is a globe valve close to the concentrated water side, and we regulate the valve and were able to get the product water or the permeate from the permeate output. Recovery ratio calculation. QFN feed flow, QPN permeate flow, QBN concentrate flow. R is recovery ratio. R is equal to 100 into QPN upon QFN. My results. We consider 1 minute and obtain the feed water volume, that is 25.26 liter. Before modification, concentrate volume 12.9 liter. Permeate volume 12.36 liter. Then recovery ratio was 48.9. After modification, concentrate volume came down to 6.21 liter. Permeate volume 19.05. Then recovery ratio enhanced up to the 75.4. Conclusion, huge benefit to the village of Megaskama by increasing recovery ratio. Reduce the cost per liter of water, reduced in feed water wastage. The feed water saving would be mostly affected on times of drought where water is scarce and feed water sources are drying up. My recommendations, if we can incorporate this improvement to the Sri Lanka Navy plants, there are 900 plants are available all around the country. We can save 1,125 tons annually. My research focus since 2015. Before 2015, Sri Lanka bought number of plants from India and Israel. The cost was 4.8 million rupees. Recovery ratio was 50%. It was energy intense process. In 2015, I developed a reverse osmosis plant here that is 1 million. Still recovery ratio of 50% energy intense. Then 2019, I developed air operated domestic reverse osmosis plant. My patent number is 21486. 2020, I again strengthened up the pre-treated system in the reverse osmosis. My patent number 21731. Today, I achieved something from my project and improved the recovery ratio up to 75%. I saved 3,600 million rupees for the country. These are the BWRO plant installation in Sri Lanka. Thank you very much. If you have any doubts, you can ask. We will answer.
Thank you very much, Commodore Dissanayake. An excellent presentation of the good work that you have done over the last several years. A good improvement to the reverse osmosis plant to get a better yield, as well as to give a benefit to the dry zone of Sri Lanka. Thank you very much for your presentation. And that concludes the 4 presentations in the first session. Now we are behind time, and actually we have only about 10 minutes for discussion, but let us put it for 15 minutes discussion time. And are there any questions in the chat box? Can you display the questions? Is it possible to display the questions?
So excuse me, may I ask a question? I'm Lieutenant Commander
Yeah, please.
Harshan Aratna, sir. So I have a question to Commodore MCP Dissanayake, sir, regarding presentation 1. So since CFD is interesting subject area, can't we make this CSD popular among our all our students? And second one is, can't we use this oscillating water column ocean wave energy converter in Sri Lanka, sir? Those are my questions.
Answering for your first question, yes, of course, we are having 50 license of ANSYS 20R in KDU. Actually, I wanted to encourage our students for the CFD. That's why I did this presentation, and we can do it. And other thing is, aeronautical department is having a wind tunnel. We can do the experiments through the wind tunnel. The same thing can be do through the CFD, and we can compare, and we can basically, being a Sri Lankans, now today the world is 3-dimensional. The theory, experiment and simulation. With our facilities, we can of course get into that 3-dimensional scenario with our available resources. For the second, answering for the second question, yes, we can start up with the oscillation water column ocean wave energy converters in Sri Lanka. From Hambantota to Panama, our wave climate is very good, and we can start up.
It's a question based on the same presentation. This comparison CFD and EFD, we know that the CFD is all about computer simulations, and the simulation results depend on how accurately you model the system, particularly the internal friction, and if there are any joints and the bends, etc. And at the same time, you have compared the results, CFD results, with EFD. How do we know which one is better? So whether the both can be correct, or the one can be more accurate than the other, or the other possibilities, both results unacceptable. How do we compare these two results? And because these results depend on how we perform these tests and the simulations.
Sir, thank you very much. And sir, for the experimental results, I did myself. Basically, I developed a vent test rig at Australian Maritime College for the King's Island. Then I obtained those results. Then what happened, my space was, the room was not enough to accommodate the pipes, the specified pipe lengths. Then what happens, I had very limited time, and I move into the CFD. CFD itself there are 3 types. If you want to get the more accurate one, you have to get research license and do it. But I did the student version. The error should be, you can compromise with 20%. But in my case, it was less than 5%. And my professor confirmed that the experimental results are meeting with the CFD results for the one pipe. That will be suffice to go for the extension one, the extended one. That's how I was did. And just after 1970s, NASA came up with this computational fluid dynamics as a 3rd dimension for the global contest. Before that, it was 2-dimensional. Those documents also says that if the percentage error is less than 20%, we can consider as that results are valid.
Thank you. Thank you for that. Thank you.
Can I follow up with for the same question, Commander Dissanayake? This is Ishani. So the difference was there, as Professor Kumaravadu also mentioned. Like, have you recognized what's the tolerable difference? Or like, if let's say that we cannot even check the experimental value, and we are totally going to rely on the computational value. In that case, we should know, like should we allow kind of a tolerance or sensitivity to the value?
Yes, you are right, Dr. Ishani. But in this particular case, for the short pipe, we did both. For a long pipe, we did CFD. And if we want to do more accurately, we can extend the dimensions of pipes and get the results and compare with the CFD.
You mean still doing an experimental study?
Actually, now everything has completed, and now they are practically installing the oscillation water column ocean wave energy converter to the Kings Island, Australia. Now it's going on.
So have you looked at the applications in Sri Lanka, and with the ocean where you are putting it, are there values to be calibrated, right?
Yes, we can. Actually, this year we set up a oscillation water column test rig here. That is a very basic one, but we did an experiment with my students, and we obtained some good results from that. If we can design and develop the similar vent test rig at KDU, we will able to get the proper details, and we can fix a oscillation water column ocean wave energy converter for Sri Lanka. It has to be multidisciplinary one, because I am a marine engineer. The electrical counterpart should be incorporate with me to do this.
Okay, thank you, Commodore.
Thank you.
Right. Thank you. In the chat box, there's a question. In the chat box, there's a question for the Waterjet paper to Commander Bogahawatte. When you check your procedure or results, how much of it is supported by literature? If not, did you find contradicting findings in literature? That's the question posed in the chat box. Commander Bogahawatte.
Yes, sir. I hope you can hear me.
Yes.
So at the Directorate of Naval Design, we have a naval architect, and one officer was particularly dedicated for the search of international literature. So he was, this project took 3 years. So he was looking for various research papers published and the manufacturer forums, and we visited boat shows, and end of this month I am also going Italy for another boat show. So all these data and the project and the papers were considered while developing our case. The thing is that in military application, no one is unclosing their critical parameters. And when we are developing a boat, our hull dimensions and the parameters cannot be given to a manufacturer. So if you need a really matching and superiority in boat manufacturing and combat the close quarter warfare, we have to do it. So we gathered all this information from different entities. As I told you, sir, we employed one officer who is good at research. He went through all the papers possible, and we visited seminars and all that. So everything was considered.
Right. Thank you very much. Thank you. And I like to pose a question to Lieutenant Commander Perera on the simulator. The simulator, you have, it's a real engine coupled with the simulator arrangement, and you have your real operation as well as the simulated operations. Now, when you are in the simulator mode, how you have modeled the mathematical modeling for parameter and other functional simulation? Do you have a mathematical model utilized for that purpose?
I hope you can hear me, sir.
Yes. Yes.
Actually, sir, it's not a mathematical model, so it's a software-driven program, but we are intending to add some intelligent function for it, like something like an artificial neural network or something like that. For up to now, it is like a program which is run when we are executing.
Right. Okay.
Yes, a quick question about this Waterjet project. And you claim an optimal design. When you say optimal, is it an improved design or an optimal design? And how do you claim this design to be optimal?
Yes, generally we need to study thrust and the waterjet speed, rather ship speed versus thrust. So hull required the power, and it I have shown the curve how it moves with the combination of hydrostatic and hydrodynamic forces. So from there we can select the engines, brake effective power, and we plot different type of engines as per requirement. But at that particular point, we don't know what is the efficiency of this operation. So we, from the universal waterjet coefficients, there's a methodology to get the efficiency plotted in this curve. I have shown the curves that we have derived, and efficiency lines comes in. So the efficiency line, the power given by the prime mover and the power required by the hull, all three are coinciding at a particular point, and that is the design point. So we were working on, let's say, engine we can't do. Engine power is we plotted, but we can improve on hull and the efficiency thereby improving, and these two parameters, the dependent parameters, we were moving here and there, and we came to a point. Generally we called as hitting the corner. So we likewise we went to that. While doing that, we have identified, now waterjets are manufacturers worldwide and are being distributed. So we will also get a common waterjet, but they don't know our hull detail and the transom detail. We understood that trimming of, rather pitching of the impeller is a possibility. So we spoke with the New Zealand waterjet manufacturer, and we gave certain parameters, and they were willing to provide the separate customer made impeller for us, for the Navy, because they are doing that. If our boat is become a superior product, lot of customers would come to us and purchase this boat. So thereby their products also be they can evolve with their purchases. Likewise, we do the highest efficiency approach.
Thank you, Commander. Actually, this kind of works must be highly commendable. A similar work is the reverse osmosis plant. I have a quick question regarding this this work. The water reverse osmosis plant. That is also another very commendable piece of work. This you mentioned about the standards comparison with the standards. Are there these standards you were referring to WHO also has set standards for water, the drinking water. That's my first short question. The second question is the value addition. I think you mentioned how the utility value, how many units will be required, the applications in military camps and elsewhere. What is the local value addition, and did you do some sort of a cost comparison of this plant developed by your team with the plants available off the shelf in the international market?
For answering for your first question, sir, WHO is given some standards for Sri Lanka, for the globe, but in our case, the Sri Lankan standards given for the Sri Lanka Water Board and Health Ministry. We are adhering with those standards. Those standards are a bit higher than WHO standards. For example, the TDS, the electrical conductivity of water, indicates the Sri Lankan standard 500. The WHO standard says 750 and above. Then our standards are much greater than the WHO standards. We are adhering with Sri Lankan standards, sir. And for the second question, the manufacturing cost, operating cost, everything, sir. Actually, I have studied and worked with the reverse osmosis plants last 25 years. Initially, the Sri Lanka Navy bought number of plants from India. 100 plants are available. Those are Rocham RO plants. I studied all those. Those are very energy intense application, and cost is very high, above 5 million Sri Lankan rupees. If you go for a 10 tons per day plant, that is more than 5 million. Then what happens? I studied all those and developed a plant in Sri Lanka Navy that was 1 million. Today, I made another plant that cost came down to 436,000 with lots of improvements, with 75% of recovery ratio. The previous plants were 50% recovery ratio. Even today, I am working with 3 of my students. The recovery ratio improved up to 98% and incorporated the solar for this system. And air-operated plant also developed through this. When we are comparing with the outside market, local market, still we are spending the least cost for the manufacturing.
Thank you very much.
I have a short question. This is Dr. Logi to verifying of Orifice plate paper. So can I go ahead?
Yes, please. Yes.
Yeah, okay, thank you. So you have talked about some meshing technologies and the mesh sizes over there in the modeling, and you have to mention the mesh size affects the error ratio. So how did you determine the mesh size, like the finer and fine or the normal mesh size while doing the simulation? That's the first question. And the second, what type of mesh technique that you have used to simulate your model? That's the second one.
The mesh was generated using ANSYS meshing 19.1 with physics and solver preference set to CFD and CFX respectively. The constraint was imposed up to 512,000 nodes and completed the fine mesh as I was indicated during my presentation. Basically, what happens, I was started with the calculation of inflation layer thickness and all the details in my Excel sheet. And with that only, I developed this measures for the pipe 1 and 2. Can you repeat your second question?
Yeah, all right. So you used what type of mesh technology? Is it a swept mesh or a triangular or tetrahedral?
I can't hear you.
Yeah, what type of mesh that you have like used, like swept mesh technique or
SST, shear stress
Oh.
transport,
okay,
turbulence.
okay. All right. Okay, thank you so
Right.
much.
Right. If there are no questions, I think
Can
we
I ask
have
one question? So
yeah, we'll take it as the last question. Right.
Yeah, I am Rangadevi here, and my question also goes to Commodore Dissanayake. So in fact, that is for your last paper. So in fact, it is very much appreciated the development that you have made. What I would like to know is now you have developed a product which seems to be at a very low cost and with high performance, and what is the possibility that we can export your product to the foreign market? Is there anything wide serving for the country?
Yes, it's a very good question. Yes, we can do, but there are two types of in RO plants. One is brackish water reverse osmosis plant, other one is desalination plants. The most of the countries are working with the desalination. For example, Australia, for example, Saudi Arabia, they are going with the desalination. That application is a bit different than what we are utilizing here. Our feed water is bit good. I told you during my presentation, and with that only we can incorporate centrifugal high pressure pump for this particular application. If you go for a positive displacement pump, the cost will be bit high, and we have to incorporate other components also. That's at this moment we can't do exporting, and but still we can go with the requirement of South African countries. They are having boreholes and they are having brackish water. Yes, we can move towards the South Africa, and we will able to fulfill if the requirement comes. Good question.
Okay, thank you very much.
Right. Thank you very much. Now we have past 10 o'clock in the morning now. Shall we conclude this session? And I thank all the 4 presenters and the other authors of the papers. Thank you very much for your excellent presentation.